Direct metal deposition is one of the critical aspect, and there may be some development happens in this additive manufacturing technology. So, but the modeling approach of direct metal deposition needs so many aspects we need to consider, and of course, and different perspective we have to look the different physical mechanism involves during this direct metal deposition process. So, of course, we just if you look into this picture, here we can see that at the same time that coaxial nozzles has been used, and that actually focusing the injecting the powder in a particular point, and of course, that which point they are meeting all this the focus point of all these 4 nozzles. Exactly at this point the laser is also focusing such that it can melt the maximum amount of the powder in that cases, and then it is deposited on the substrate. So, this basically in direct metal deposition technique, there we need to control that powder flow rate. At the same time we need to focus need to control the heat source, and mostly in these cases either we can use the laser beam heat source or in few cases we can use the electron beam also. But of course, this technology actually having some similarity of laser cladding process also, because in the laser cladding process also we can similar philosophy use for the development of making some cladding system on the surface, and on this surface basically to inject throw the powder on the surface, and then after that we just focus the any kind of laser source such that there may be some layer deposition may happens at the same deposition as well as melting of the deposited powder particles happens, and most of the cases the laser cladding system normally use to repair a damaged part. So, similar principle can be used, but probably in this case it is a more controlled way we need to look into as compared to the laser cladding process, such that some building up of a particular object can be done in layer by layer deposition process. So, therefore, interaction of the nozzle system and the continuous laser beam is one of the major aspect to optimize the position of the laser focused beam as well as the coaxial lasers. So, nozzle usually coaxial to moving, but at the same time it is coaxial, but it moves in a particular direction. So, there is therefore, both nozzle and the laser beam together moves, that kind of strategy we need to cover, and at the same time we have to look into that during moving the typical oil profile zone looks like the double ellipsoidal. So, most of the cases we observe in case of the moving laser welding or any kind of arc welding processes, the typical shape is more or less equivalent to the nature of the double ellipsoidal. So, by just looking into that kind of beam profile, we can optimize the laser scanning speed, and of course, the powder feed rate, all gas shielding gas pellet, all parameter also we can optimize. So, we look into that what are the typical aspects we have to consider for the development of the direct metal deposition technique. So, therefore, I am just mentioning the typical area direction where we need to focus on that. First, calculation of the temperature distribution in the coaxial powder stream. So, in the coaxial powder stream, the calculation of the temperature profile we have to ensure such that if we estimate the temperature profile at exactly which location when the powder is traveling, maybe at which location it starts melting, and of course, maybe at which area that there is may not be the melting of the powder or partially melting of the powder may also happen. So, that can be decided first using to develop this DMD technology. So, therefore, of course, prediction of the projected area by powder. So, when powder is projecting a particular area, what is the projected area and which projected area we are focusing, that information is also required, and of course, it depends on the geometric shape and size of the nozzle. The nozzle can decide what may be projected area, and of course, powder flow rate. So, what is the powder flow rate and what we are mixing the powder and shielding gas, such that it can create some specific area projected area, and accordingly we can decide what is the laser focus diameter on this projected area. And of course, other parameter, for example, distance from the nozzle also influence all these things. If we look into this schematic diagram, we can see that nozzles are there, and from the nozzle there is a powder is coming along with the sealing gas, of course with certain pressure and with certain flow rate it is following. And since one just come out of the nozzle, so the beam actually diverge, and it actually this indicates that actually this is the projected area. So, on the surface, of course, this projected area on the surface may be, if it is a flat surface, so it is easy to handle the estimate the projected area, and accordingly we can take the decision the what may be powder flow rate and focus diamond. But at the same time, if it is a kind of concave or convex type of surface over which powder is actually throwing, in that cases we have to be more careful to choose the proper parameters just by looking into the projected area of the powder on the surfaces. So, see here you can see that it is a moving system, that means nozzle as well as the laser source is moving in a particular velocity, and at the same time sealing gas flow rate also there, and accordingly this projected area may be this may not be very circular, rather I say that this projected area may be elliptical in sense. So, that depends, we are able to predict these things just looking into this moving. If we consider the moving source, what way we normally tackle the moving heat source problem in case of welding processes. Similar we can tackle this DMD technology also, and of course it is possible to estimate what is the projected area for a moving laser or for moving powder flow rate for a moving powder. So, in that cases we have to consider the effect of the velocity with similar strategy of the welding process. So, definitely finally prediction of the width and deposition of the heights after melting, that is the ultimate objective for a particular development of a printer, metallic printer, such that we will be able to predict what is the width and what is the height and maybe what is the surface roughness, or finally we can it can decide what is the resolution of this printer. So, that means what surface finish we can expect from this particular scene by optimum setting of all these parameters. Now, that is what domain 1. Of course, the domain 2 means that once we projected the powder on a particular surface and then powder is melted, and of course, this what is the molten zone dimension and the solidification, melting and solidification behavior on the laser path, or of course, these lasers will become more complicated when it is under a moving laser source. So, that path, prediction of this path, the shape, size of the molten zone, heat affected zone, and that is more important. So, path can be linear or curved path. So, laser can be moved, but depending upon the geometric shape, it can be some curved path. So, based on that, we can the temperature, prediction of the temperature distribution is important in any kind of modeling approach. All these things, shape and size of the molten zone as well as the heat affected zone is also necessary to predict, and of course, solidification time such that we can decide the gap between the successive layers based on the solidification time. Of course, mass addition to the solution domain, because the within the solution domains in the domain 2, that means where we are trying to analyze the temperature distribution. So, there is a continuously powder is adding. So, therefore, mass is adding to this domain. So, that we have to take care, we need to incorporate that effect of this domain. And of course, although the material is not very superheated condition, but till fluid flow consideration may be significant, and that increase the prediction of the temperature distribution. So, therefore, fluid flow can also be included in the domain 2, where we are trying to analyze the temperature distribution. Of course, if we use any kind of surface active elements within the material may change the molten pool shape and size. So, in that cases probably fluid flow will help to actually determine the shape and size of the molten pool, or specifically during when powder is actually projected, and after projection we just the powder is basically melting on a in domain 2. So, therefore, all this prediction is necessary to decide or to select the optimum range of the parameters for the development of the DMD technology. So, therefore, some modeling approach having some influence, if we look into incorporate all the physical phenomena in the modeling approach, that can help to take some decision for the setting of the parameters in a direct metal deposition techniques. But some practical information about the direct metal deposition techniques is maybe useful when you try to develop some kind of the metallic printer. So, first, existing the nozzle, the powder particles are drawn, basically powder particles is drawn downward to the action of the 3 factors. So, thus physically the gravity force is important, momentum of this from the transport gas. So, momentum, because their powder is not carried just only by gravity, because there is some transport gas mixed with the powder, such that this transport gas actually carry the powder to the desired position. So, it will be easy to project in a particular position, and momentum from the secondary gas flow, secondary there, apart from this transport gas, we use the shielding gas as well also during this. So, momentum of the shielding gas also helps to decide the final shape and size of the deposited layer, their thickness and surface roughness also. So, therefore, actually one gas stream is directed to the molten pool, that one gas stream, along with the powder is basically directed, and the shielding gas just protect the molten pool. Of course, the momentum from the shielding gas also influence the surface roughness produced, that is basically will be able to know after the solidification of this particular zone. So, therefore, the shape of the gas powder stream, what are the shape particular and projected area exactly on the surface, combined with the size of the molten pool and have a large influence on the size and shape of the built up. So, the shape of the gas powder stream, that stream, and of course, size of the molten pool all actually influence on the size and shape of the build up area. Basically, that decides the build up area or size and shape, then width and thickness of build up area also, as well as the powder efficiency, because if we project the powder beyond that beyond the molten pool zone. So, most of the cases there is a wastage of this powder without melting these things. So, therefore, powder efficiency is also important to analyze all this effect, and therefore, determine the geometrical accuracy, and that actually decides the geometrical accuracy and surface roughness of the built up. So, therefore, that is also an important part of the DMD technology. So, the shape of the gas powder stream is basically tailored by the nozzle geometry. So, definitely the shape of the gas stream powder basically decided by the nozzle geometry, by the angle, making the nozzle angle with respect to the vertical axis, and the distance between from the molten pool to the basically stand up distance, molten pool in the nozzle exists, and of course, the gas velocity from the primary and secondary flow. Primary flow is the gas velocity of the transport gas, and secondary flow basically the shielding gas. All this flow actually you need to track or need to analyze to correctly predict the geometrical accuracy of the built up in case of direct metal deposition technique. So, we have discussed that different metal printing technologies mostly focus with the metallic printing processes. There is a development of different area, maybe arc based metallic printing or maybe powder based metal printing processes. We have already discussed or maybe mainly focused on this module. But overall, if you look into the 3D metal printing process, it is having several challenges to develop. First is the high cost of materials. It is a overall aspect we are trying to look into that. First, high cost of materials due to maintaining the purity of the particles. So, of course, when you are using the powder particle, so it is always necessary to maintain the purity of the particles and require particle shape and size. So, two aspects, that purity of the particles, and second is the particle shape and size is very much important, that actually decides the surface roughness we can achieve during the metal printing technology. So, therefore, in that case So, if you want to the purity of the particles, production of the pure particle to maintain the purity of the particles and with a particular very small size, then powders becomes more costly as compared to the materials. Most of the cases there is a chances of the maybe in the formation of the oxides. So, therefore, unreliability of the machines. So, of course, the actually the metal printing process, the domain of the parameters exist in the very narrow domain. So, range is very narrow. So, therefore, in that sense maybe there is a not much scope exactly to vary all the parameters over a wide range, and even it is not for a narrow range as well also, and of course, this depends on the different machines to machines. So, that is in that sense the reliability of the machines of a particular metal printing process is questionable, and most of the cases we can assume that it is a 20% rejection rate when you try to develop some kind of product. Of course, till there is a research is going on for the development of these machines. So, of course, challenges scaling up the technology. So, maybe a very small component size, the surface roughness we can achieve very good surface roughness, and maybe in that amount of the surface roughness may be sufficient if the component size is very small, but when we try to produce a very bigger component probably may not be very economical using this laser based or electron beam based metal printing technology. So, in that case probably large volume, when there is a large volume deposition is required, probably arc based additive manufacturing technology may be more suitable in that case. So, speed of the product manufacture. So, of course, if you try to achieve high resolution of a printer, if you want to achieve or to achieve very good surface finish, then speed of the machining, speed of the process to produce a particular product using the 3D metal printing technology is little bit less as compared to the other conventional techniques. So, therefore, time constant or maybe large amount of the time is required to produce a particular build up a particular component, that is also one constant or one challenge in the 3D metal printing technology. And of course, environmental concerns, because handling the powder are maybe sometimes difficult, and that may be related to environmental concerns. Anyway, if you try to look into that metal printing technology using the other conventional method also, definitely in other cases also may be some kind of environmental issues also there. And since using the laser we are melting the components and it is above melting point temperature. So, some contamination to the or maybe some that we are using the shielding gas also. So, that contribute to the environmental pollution or maybe health hazards to handling this technology. So, therefore, in that sense environmental concern it may be important in this cases. So, surface finish is one aspect. So, surface finish depends on the intuitively on the process parameter, what is the particle size we are using, and if you look into the other way also, if you try to reduce the size of the particles, then cost of manufacturing of the powder particles will increase. So, therefore, in that sense surface finish, achieving a surface finish without machining by using additive manufacturing technology is really a challenging task. A resolution of the printer, of course, resolution of a printer means how fine surface finish we can achieve using in a particular or how exactly replicate the CAD the geometry of a particular object, and that depends on the that decides the resolution of a printer. Therefore, to achieve the very high resolution, of course, the maybe built up size can be reduced, or in the other way also powder particles can also be reduced to achieve all these things. So, mechanical properties probably layer by layer deposition. So, in that cases it may not be achieved the all homogeneous mechanical properties or isotropic mechanical properties, and may not be possible using this additive manufacturing tool. So, that is the one concern to achieve isotropic material properties in case of layer by deposition process. And of course, most of the process is associated with some post processing to get a desired surface finish. So, definitely that is one of the limitation of the 3D metal printing processes. So, thank you very much for your kind attention.